Now, picture this: a barren stretch of the Arizona desert under a white-hot afternoon sun where the horizon shimmers with dry, dizzying heat. The modern power grid is trembling under the massive electrical load of thousands of air conditioners screaming at full capacity. Across the country, the hum of mechanical cooling is the only thing keeping modern life from grinding to a halt. Yet, nestled in the arid hills, an abandoned 19th-century building stands silent and cool, operating entirely without a power cord, a generator, or a monthly utility bill. For decades, stories have circulated about early desert dwellers who managed to keep their shelters remarkably comfortable in the middle of summer, using nothing but the wind and a hollow vertical shaft. Many dismiss these accounts as romantic frontier folklore, an unscientific myth from a bygone era before modern air conditioning made desert living easy. But the truth is far more fascinating. In 1995, the Environmental Research Laboratory at the University of Arizona conducted a rigorous scientific evaluation of passive cooling towers. The results were startling. The researchers documented an interior temperature of exactly 75 degrees Fahrenheit, while the outside air baked at 106 degrees Fahrenheit, all achieved with zero electricity. This design was not a spontaneous invention of the American frontier. Its roots reach back over 3,000 years to the ancient Persian badgir's grand, chimney-like windcatchers that rose above the desert skyline to capture high-altitude breezes and channel them deep into stone dwellings. When miners arrived in the American Southwest during the 1880s, they adapted these ancient principles to the brutal conditions of Tombstone and Death Valley. But there is a reason these ancient cooling shafts are not standard features on modern suburban homes. The physics that allow a passive windcatcher to pull heat out of a building are incredibly powerful, so powerful that they can easily turn a home into a silent, deadly trap. If you build one of these shafts without understanding the delicate pressure boundaries of your home, the chimney will act as a giant vacuum, reversing the draft of your wood stove or gas heater and pulling lethal, odorless carbon monoxide straight into your bedroom. To understand how to harness this ancient cooling method safely, we have to look past the surface and examine the hidden thermal mechanics of the desert. We must analyze how those early miners survived, why modern green building designs often fail to replicate their success, and how a basic understanding of fluid dynamics can yield a completely silent, zero-energy cooling system that operates in absolute harmony with the natural environment. To truly grasp the genius of the old miners, one must first experience the absolute hostility of a Southwest desert summer. In places like Tombstone, Arizona, or the deep basin of Death Valley, summer is not merely a season, it is an active, crushing weight. The air is so dry that moisture evaporates from your skin before you can even register that you are sweating. The ground beneath your feet absorbs the relentless solar radiation until the dirt itself reaches temperatures of over 140 degrees Fahrenheit. Here's what everyone missed. Modern houses are fundamentally built to fight this environment rather than cooperate with it. Standard Western construction relies on lightweight wood framing, fiberglass insulation, and thin drywall. This method works reasonably well in mild climates, where mechanical heating and cooling can easily correct minor temperature swings. But in the extreme desert, this structure acts like a giant thermal sponge. Throughout the day, the intense sun beats down on the roof and walls, slowly saturating the thin insulation. By mid-afternoon, the walls have absorbed as much heat as they can hold, and they begin to dump that stored thermal energy directly into the living spaces. Think about that for a second. When you go to bed at 10 o'clock at night, your air conditioner is not just fighting the outdoor air. It is fighting your own walls, which are radiating midday heat like a massive toaster oven. This is the phenomenon of thermal saturation, and in a lightweight modern home, it creates a constant uphill battle. Homeowners attempt to solve this by installing larger air conditioning units and turning up ceiling fans. But a ceiling fan does not cool the air, it merely moves it. If the air in your room is 90 degrees, a ceiling fan simply blows 90-degree air across your skin. In fact, in an uninsulated attic space, A poorly placed fan can actually depressurize the ceiling, pulling superheated attic air down through light fixtures and drywall seams directly into your living room. It is a cycle of mechanical failure that requires constant electrical inputs just to remain barely habitable. Let that sink in. We have built an entire civilization in the hottest regions of the continent on the assumption that the electrical grid will never fail. But the early miners of the 1880s did not have the luxury of a grid. They had no electricity, no manufactured ice, and no insulated panels. When the silver boom drew thousands of fortune seekers to the dry hills of southern Arizona, they were forced to confront a climate that was actively trying to kill them. The miners quickly discovered that their traditional canvas tents and wooden shacks were unlivable ovens during the day. However, deep underground, the reality was entirely different. As they descended hundreds of feet into the earth to excavate the rich veins of silver, they noticed a strange and welcoming phenomenon. Even when the surface temperature was climbing past 110 degrees, the air deep inside the mine shafts remained cool, stable, and surprisingly fresh. This was not magic. It was the physics of the Earth's natural thermal mass. At a certain depth, the temperature of the ground ceases to fluctuate with the seasons, remaining at a constant, cool baseline of around 60 degrees Fahrenheit. But the miners also noticed something else. In certain shafts, there was a continuous, powerful breeze blowing through the dark tunnels, even on completely windless days. By examining the journals and letters of these early engineers, we can reconstruct their breakthrough. They realized that the air movement was caused by a natural pressure differential. A deep, vertical shaft exposed to the hot sun at the surface would warm up, causing the air inside the top of the shaft to expand, become less dense, and rise. This rising column of hot air created a gentle, localized vacuum at the bottom of the mine. If that shaft was connected to another, shaded opening further down the hill, the cool, dense air from the lower opening would be drawn into the tunnels to replace the rising hot air. They had accidentally created a massive, subterranean air pump, powered entirely by the sun and the geometry of the Earth. The miners began to ask a simple question. Could this same principle be applied to a domestic dwelling on the surface? They began experimenting with primitive, vertical flues built onto the sides of their adobe cabins. Adobe, a traditional building material made of clay, sand, and straw, possesses an incredibly high thermal mass. Unlike wood, a thick adobe wall can absorb solar radiation for several hours before that heat reaches the interior. This is known as thermal lag, which typically lasts between 6 and 8 hours in a well-constructed building. The miners realized that if they combined this slow-heating adobe shell with a vertical ventilation chimney, they could create a continuous, self-regulating cooling cycle. During the day, the intense heat of the sun would beat down on the chimney, warming the air inside it and forcing it to rise out of the top. This, in turn, pulled cooler air into the cabin from shaded, low-level intake vents or subterranean crawl spaces. The numbers don't lie. While the occupants of standard wooden frame shacks were suffering in indoor temperatures that often exceeded 105 degrees, the miners who adapted these chimney flues to thick adobe shelters were enjoying indoor temperatures in the mid-70s. They did not need a single watt of electricity, nor did they require complex machinery. They had simply learned how to use the extreme desert heat to drive a natural, convective cooling loop. But as effective as these historic systems were, modern attempts to recreate them often run into unexpected, dangerous hurdles. The physics of natural draft are simple, but when you bring these forces into a tightly sealed modern home, the margin for error disappears. To build a system that works without endangering your life, you have to understand the precise balance between thermal dynamics and structural safety. To build a passive cooling network that functions reliably in the harsh, dry climates of the Southwest, we cannot rely on the forgiving margins of modern electrical fans. We must understand the literal weight of air, the drag of friction, and the delicate thermal storage of earth and stone. The old miners of Tombstone did not have access to manufactured plastic or high-efficiency blowers. They worked with shovels, local timber, native stone, and the fundamental laws of gravity. To replicate their success, we must start deep beneath the Earth's surface, where the ground acts as a massive thermal battery, insulated from the sun's daily assault. The first step in constructing an integrated passive cooling loop is the installation of subterranean air flues, often called earth tubes, which function as the home's pre-cooling intake network. The earth at a depth of 8 to 10 feet maintains a nearly constant temperature year-round, typically hovering between 55 and 60 degrees Fahrenheit. To tap into this stable temperature sink, we must excavate a series of deep trenches. In these trenches, we lay smooth, heavy-walled conduits. It is a common mistake in modern off-grid builds to use cheap, corrugated agricultural pipe for this purpose, but that is a recipe for system failure. The interior ridges of corrugated pipe create immense boundary layer friction, slowing the passive movement of air to a crawl. Even worse, those ridges trap moisture from condensation, creating stagnant pools that invite mold, bacteria, and musty odors directly into the ventilation stream. Instead, we use thick-walled, smooth-bore piping with a diameter of at least 12 to 15 inches. This wide, smooth passage minimizes surface friction, allowing air to glide effortlessly through the earth. The length of these subterranean tubes is a delicate balance of thermodynamics. If the tube is too short, say, less than 75 feet, the air will pass through too quickly, exiting into the house before it has had enough time to transfer its heat to the surrounding earth. If the tube is too long, stretching past 150 feet, the cumulative friction of the pipe walls will choke the draft entirely, stalling the air before it ever reaches the dwelling. The sweet spot for a standard residential layout is a run of approximately 100 feet, sloped gently downward away from the house at a grade of 1%. This slope is critical. It ensures that any condensation that forms as warm air cools down inside the pipe will drain safely into a gravel-filled dry well at the lowest point, preventing mold growth and maintaining clean, fresh air. At the far end of this subterranean pipe, we construct the low-level intake plenum. This is where fresh outdoor air enters the loop. It must be positioned in a heavily shaded area, ideally under the canopy of deep-rooted trees or on the northern, cool side of the building, and elevated at least 3 feet off the ground to prevent dust and ground-level debris from being sucked into the intake. While the subterranean tubes pre-cool the incoming air, the true engine of this entire system is the southern-facing solar updraft chimney. This is the vertical stack that creates the low-pressure draft required to pull air through those 100-foot underground tubes. The physical construction of the solar chimney requires absolute precision. It is built as a tall, narrow shaft on the south-facing exterior wall of the home, rising at least 6 feet above the highest peak of the roof to catch the full, unobstructed force of the midday sun. The front of this chimney is covered in double-pane tempered glass, which acts as a greenhouse, trapping solar radiation inside the shaft. Directly behind the glass is the absorber plate, a heavy sheet of corrugated metal painted with a high-temperature, flat black coating. When the sun hits this black metal plate, it absorbs nearly 95% of the solar radiation, heating up rapidly. The air in the narrow gap between the black plate and the glass is superheated, expanding and rising rapidly toward the top exhaust vent. The width of this internal air gap is the single most critical variable in solar chimney design. If the gap is too narrow, less than 3 inches, the rising air will experience high friction against the glass and metal, restricting the airflow velocity. But if the gap is too wide, stretching past 8 inches, a dangerous thermodynamic phenomenon known as reverse looping occurs. In a wide channel, the hot air rising along the black metal plate will pull cooler air down the inner face of the cold glass, creating a closed, circular convection loop inside the chimney itself. This internal loop destroys the chimney's draft, stalling the ventilation of the home and trapping heat inside. For a vertical residential chimney, the mathematically optimal air gap is exactly 4 to 6 inches. This narrow channel forces the rising air into a tight, laminar flow, maximizing upward velocity and creating a continuous low-pressure zone at the base of the chimney. To ensure that the intense heat generated inside the solar chimney does not migrate backward into the living space, the back wall of the chimney stack must be insulated to an extreme standard, ideally a minimum rating of R15. This thermal barrier is constructed using foil-faced rigid foam panels sealed with high-temperature aluminum tape, ensuring that every BTU of solar energy is channeled upward to drive the ventilation loop rather than bleeding back through the walls into the home. At the very top of the solar chimney, we construct the exhaust cowl. This cowl must be designed to shield the opening from crosswinds while simultaneously harnessing the Bernoulli principle. By shaping the exhaust hood like a gentle venturi, passing wind will create a secondary low-pressure zone right at the exhaust point, further accelerating the hot air out of the chimney. But during the hottest days of midsummer, when the desert air is dry and baking, thermal draft alone might not be enough to achieve comfort. This is where we integrate the ancient Persian badgir concept, the downdraft evaporative cooling tower. This tower is built on the windward side of the structure, rising high into the sky to capture prevailing breezes. At the top of this tower, we construct a wet pad chamber. The old miners utilized thick, porous clay pots or heavy canvas bags filled with water, allowing the moisture to slowly seep through the material. In a modern adaptation, we use high-efficiency, textured cellulose cooling pads supplied by a low-power, 12-volt water pump connected directly to a small solar panel. As dry, hot desert wind enters the top of the tower, it is forced through these damp cooling pads. The hot air immediately transfers its sensible heat to the water, causing the water to evaporate. This process of latent heat transition drops the temperature of the airstream dramatically often, by as much as 15 to 25 degrees Fahrenheit in a matter of seconds. As the air cools, it becomes significantly denser and heavier than the hot air surrounding the tower. Gravity takes over. The heavy, cool air drops down the vertical shaft of the tower, spilling out of the low-level vents into the living room like an invisible, cool waterfall. To tie this entire system together, we must install a system of heavy, insulated bypass dampers at the entry and exit points of both the solar chimney and the cool tower. These dampers are constructed from wood panels sandwiched around 2 inches of rigid foam insulation, fitted with thick EPDM rubber gaskets to ensure an airtight seal when closed. During the winter months, or during sudden dust storms, these dampers are sealed tight using a system of manual, weighted lever locks. This allows the homeowner to completely isolate the house from the passive chimneys, preventing cold winter drafts from entering or precious interior heat from escaping up the exhaust stack. Every connection, every seam, and every joint in this passive network must be sealed with meticulous care. In a standard house, air leaks through window frames, outlet boxes, and ceiling joints. But in a passive draft home, these random leaks act as competitive drafts, short-circuiting the system. If the solar chimney can pull air through a leaky kitchen window, it will stop drawing air through the 100-foot underground earth tubes, destroying the pre-cooling cycle. The building envelope must be sealed to a high standard of airtightness, ensuring that the only way air can enter or exit the home is through the engineered, mathematically calculated pathways of our passive system. Only when this physical infrastructure is perfectly balanced can we begin to look at the deep physics of air pressure and the critical safety boundaries that govern this style of architecture. To transition from the physical components of this system to the invisible forces that govern them is to step into the realm of fluid dynamics. We must realize that a passive home is not a static object. It is an active, breathing pressure vessel. The air inside is constantly shifting, expanding, and seeking equilibrium according to the laws of thermodynamics. If we do not respect these laws, the very forces we harness to cool our living spaces can easily compromise the safety of our homes. At the heart of all passive ventilation lies the ideal gas law, the fundamental rule of physics, where pressure, volume, and temperature are bound in a delicate, shifting ratio. When solar radiation warms the air inside our vertical solar chimney, it forces the molecules to move faster, push farther apart, and expand. As this air expands, its density decreases relative to the cooler, denser air outside the structure. This density difference is what drives the stack effect, a phenomenon governed by a simple but powerful mathematical relationship. The pressure difference that drives our draft is determined by the height of the chimney multiplied by the gravitational constant multiplied by the difference between the density of the outside air and the density of the inside air. In simple terms, the taller the chimney and the hotter we can make the air inside it, the greater the pressure differential we create. But this pressure differential is not just pushing air out of the top of the chimney, it is actively pulling air from the base. A properly functioning solar chimney behaves like a continuous, low-power vacuum cleaner, constantly drawing air out of the building's interior. This means that when the system is operating at peak efficiency in the middle of a hot summer afternoon, the entire living space of the home is under a state of mild negative pressure relative to the outdoors. In a modern, highly sealed home, this negative pressure is where extreme danger begins. If your home contains any traditional fuel-burning appliances such as a wood-burning stove, a propane space heater, or a gas-fired water heater, they rely on a natural, upward draft to carry dangerous combustion gases safely out of the house. These appliances operate on a very delicate pressure balance. The hot exhaust gases from a wood fire rise up the metal flue because they are lighter than the indoor air. However, if your solar chimney is pulling air out of the house faster than fresh air can enter through the subterranean tubes, the negative pressure inside the home will act as a stronger vacuum than the draft of the stove's chimney. The natural flow of the heating flue will stall. Then, it will reverse. Instead of rising safely out of the roof, the heavy, soot-laden smoke and invisible odorless carbon monoxide will be sucked backward down the chimney flue directly into your living room, a process known as flue reversal. Carbon monoxide is a silent, lethal hazard that binds to the hemoglobin in your blood, depriving your vital organs of oxygen without your ever realizing anything is wrong. If this reversal occurs while the occupants of the home are asleep, the results can be catastrophic. To eliminate this risk, we must establish 3 non-negotiable engineering mandates for any home utilizing passive convective drafts. The first mandate is the complete isolation of the combustion air supply. No fuel-burning appliance inside the home should ever draw its combustion air from the indoor living space. Instead, the wood stove or gas heater must be equipped with a dedicated, direct-ducted external combustion intake. This is a sealed, metal duct that runs from the outdoors directly into the sealed firebox of the appliance. This ensures that the fire has a constant, abundant supply of oxygen to burn efficiently, but the air loop feeding the fire is completely isolated from the pressure dynamics of the house. The vacuum created by the solar chimney cannot pull air from the wood stove because the stove is a closed, airtight circuit, pulling its air from outside and venting its exhaust back outside. The second mandate is the absolute physical separation of the active draft flues. The exhaust cowl of the solar chimney and the discharge flue of any heating appliance must be located on different sides of the roof, separated by a substantial distance, ideally a minimum of 10 to 15 feet, and designed so that prevailing winds cannot carry exhaust smoke into the intake of the cooling tower. Furthermore, the passive cooling tower intakes must be positioned far below the level of any potential exhaust vents, ensuring that there is zero risk of re-entraining toxic gases back into the fresh air stream of the home. The third mandate is the implementation of multi-level digital carbon monoxide monitoring. Because passive houses rely on natural air movements that can change with wind direction, temperature swings, and open windows, manual monitoring is not enough. Digital, battery-backed carbon monoxide alarms must be permanently installed on every level of the structure, particularly in or immediately adjacent to all sleeping quarters. These alarms must be tested monthly and replaced according to the manufacturer's strict guidelines. They act as our final, vital line of defense against the invisible dangers of draft reversal. Beyond the major hazards of combustion, we must also consider the subtle pressure battles that occur within the interior of the home itself. When we design a passive cooling loop, we map out a continuous pathway for air to travel, entering through the subterranean tubes, flowing through the main living spaces, and exiting up the solar chimney. But what happens when an occupant closes a bedroom door? A closed interior door acts as a sudden, massive dam in the fluid pathway. The room containing the closed door is immediately isolated from the passive draft loop. The air inside stalls, rapidly absorbing heat from the walls and becoming stagnant and stuffy. Worse, if that bedroom has an open window, the solar chimney on the other side of the house may attempt to pull air from that room anyway, creating a highly localized negative pressure zone that can cause localized draft failures or draw hot, unconditioned air into the house through wall cracks. To resolve these interior pressure imbalances, we must install transfer grills or baffled door vents in all interior walls and doors. These vents are designed to allow air to pass freely between rooms, maintaining pressure equilibrium throughout the entire home, while utilizing internal baffles and sound-absorbing materials to block the transfer of light and noise between private spaces. This ensures that even when a door is closed for privacy, the passive cooling draft can continue to flow unhindered. Finally, we must address the regulatory landscape. Many owner-builders are surprised to find that building inspectors and local planning departments are highly skeptical of passive draft designs. Modern building regulations, such as those established by the American Society of Heating, Refrigerating, and Air Conditioning Engineers, are written with the assumption that every home will have a mechanical ventilation system with a predictable, fan-driven air exchange rate. These standards are designed to protect public health by ensuring a minimum number of air changes per hour to dilute indoor air pollutants, such as volatile organic compounds, moisture, and carbon dioxide. Because passive solar chimneys and windcatchers rely on variable weather conditions, they do not provide a constant, uniform flow rate. On a calm, overcast day, the draft may drop significantly, failing to meet the strict prescriptive requirements of modern codes. To bridge this gap and secure legal permit approval, we must design our systems as hybrid networks. We install low-draw, highly efficient inline backup fans inside our subterranean ducts and solar chimney bases. These backup fans are connected to automated sensors that monitor indoor air quality and temperature. If the natural convective draft drops below a safe threshold, or if indoor humidity rises too high, the automated system activates the low-wattage fans to assist the draft, ensuring constant, code-compliant ventilation, while still operating on a fraction of the energy required by standard air conditioning. By combining the natural, elegant physics of the old miners with modern, direct vent safety engineering and automated hybrid backups, we can create a home that is incredibly efficient, completely comfortable, and, above all, structurally and chemically safe for our families. The high desert of the American Southwest is a landscape defined by extreme, almost violent transitions. In the span of a single afternoon, the same environment that baked under a 100-degree sun can be swept by a freezing cold front tumbling down from the northern mountain peaks. For a homeowner living entirely off the grid, this sudden shift is not just an inconvenience. It is the ultimate test of their building's thermodynamic design. As the autumn sky darkens to a heavy, bruised purple, the wind shifts from a gentle southern thermal draft to a roaring northern gale, carrying the first icy flakes of a record-breaking early blizzard. Within hours, the ambient temperature plunges by over 50 degrees Fahrenheit, and the passive cooling structure must undergo an immediate, absolute physical transformation to survive. In a traditional home, surviving a blizzard simply means turning up the thermostat and letting a mechanical furnace burn through fossil fuels to combat the cold. But in a passive draft home, a sudden freezing storm presents a unique and immediate crisis. The entire house has been engineered to encourage air movement, to pull air through subterranean tubes, pass it through evaporative chambers, and vent it out of a tall solar chimney. If left open, this powerful convective loop will continue to run in reverse, drawing sub-freezing, moisture-laden air directly into the heart of the living space and turning the home into a domestic deep freeze within minutes. The first line of defense in this environmental emergency is the manual sealing of the passive towers. The homeowner must move quickly to close the heavy insulated dampers at the base of the cool tower and the top of the solar chimney. This is where the physical engineering of the dampers is put to a brutal test. During the summer, these dampers remained open to the moving air. But now, they must provide an airtight, pressure-resistant seal against the freezing gale. Many modern builders who attempt to replicate passive designs make the mistake of using standard, thin sheet metal sliding dampers. In a freezing storm, these metal panels quickly become cold bridges, transferring sub-zero temperatures directly into the home and causing condensation to form on the indoor side. This condensation soon freezes, locking the damper in place and tearing the delicate rubber seals. To prevent this failure, we must look to a design adapted from the mining camps, the weighted mechanical lever lock damper. These panels are constructed with a heavy core of rigid foam insulation, sandwiched between two layers of marine-grade plywood, providing a thermal resistance rating of at least R10. The edges are lined with thick, compressible EPDM rubber bulb seals. When the control lever is pulled, it does not slide. It swings on a heavy steel hinge, utilizing mechanical advantage to press the damper face flat against the solid wood frame. This movement compresses the rubber seals evenly across their entire surface, creating an airtight barrier that can withstand the intense external pressure of the storm winds without leaking a single cubic foot of sub-zero air. As the blizzard intensifies outside, piling snow against the southern glazing of the solar chimney and crusting the cool tower intake in thick layers of frost, the homeowner initiates the heating phase. The primary heat source is a heavy, cast-iron wood-burning stove situated at the center of the home's high-mass adobe walls. This is the moment where the critical safety physics of our direct vent design are tested under the most extreme atmospheric conditions. Outside, the wind is howling across the roof peak at over 60 miles per hour. According to the Bernoulli principle, high-velocity wind passing over a surface creates a localized zone of extreme low pressure. In a standard house with a traditional wood stove, these high-velocity winds whipping across the chimney cowl can create a powerful, fluctuating suction that pulls the fire's draft upward too quickly, causing the stove to burn out of control and wasting precious firewood. Conversely, if a sudden wind gust hits the chimney from a specific angle, it can create a localized high-pressure zone that forces smoke and deadly carbon monoxide backward down the flue into the living room. But our system is immune to these dangerous pressure swings. Because the wood stove is equipped with a dedicated, completely isolated external combustion air intake duct, the entire combustion loop is a closed, balanced circuit. The air that feeds the fire is drawn directly from the outdoors, passes through the sealed combustion chamber, and is exhausted out of the vertical flue. The internal pressure of the home, which remains stable and sealed behind the closed, high-efficiency dampers, has zero influence on the fire. Even as the external winds fluctuate wildly, creating massive pressure deltas across the roof, the draft of the wood stove remains perfectly stable, burning cleanly and efficiently, without pulling a single molecule of indoor oxygen. Inside the quiet living room, the digital carbon monoxide alarm sits at a comforting 0 parts per million. Despite the raging blizzard outside, and despite the fact that a hot wood fire is burning at the center of a highly insulated, sealed structure, there is no risk of flue reversal. The pressure boundaries of the home are secure, and the family can sleep in absolute safety, completely isolated from the toxic combustion gases. As the night deepens and the outdoor temperature drops below zero, a second thermodynamic phenomenon begins to work in the homeowner's favor: the slow release of stored thermal energy from the building's internal mass. Throughout the late summer and early autumn, the thick adobe and stone core of the home absorbed heat during the day and released it at night. Now, as the wood stove burns, the intense, radiant heat from the fire is slowly absorbed by these same high-density walls. Because adobe has a high specific heat capacity, it does not heat up instantly. Instead, it acts like a giant thermal battery, storing the energy of the fire deep within its dense clay molecular structure. This is the beauty of thermal lag. Hours after the wood fire has died down to a bed of quiet embers, the thick interior walls continue to radiate a gentle, consistent warmth outward into the rooms. The indoor temperature remains at a stable, comfortable 68 degrees Fahrenheit, even as the storm outside drops the outdoor air to sub-zero levels. The home has transitioned from a highly efficient heat rejection engine in the summer to a highly insulated heat retention envelope in the winter, all without the assistance of a single computer chip, electrical valve, or grid connection. When the morning sun finally breaks through the dissipating storm clouds, reflecting off the deep snowdrifts that bury the desert floor, the homeowner can open the dampers of the solar chimney once again. The bright morning sun hits the black absorber plate, quickly heating the air inside the glazed shaft and restarting the gentle, passive ventilation cycle, purging the stale indoor air and replacing it with clean, crisp, sun-warmed desert breeze. The trial is over. The physics of the old miners, coupled with modern safety engineering, have proven that a home can cooperate with the most hostile climates on Earth, keeping its occupants safe, warm, and secure in the face of nature's most extreme volatility. To move past the theories of thermodynamics and the stories of frontier survival is to stand before the cold, unyielding testimony of physical data. In the world of off-grid engineering, speculation is a liability. Only empirical measurements can validate a design. By examining the sensor logs of a fully operational passive cooling home over a 72-hour midsummer trial, we can see exactly how these invisible currents perform when subjected to extreme desert heat. Imagine stepping across the physical threshold of this structure on a July afternoon. Outside, the world is a blinding, heat-saturated expanse, where the air temperature has reached 106 degrees Fahrenheit. The dry wind feels like a blast from a furnace, and the ground-level heat is almost unbearable. But as the heavy, sealed entry door swings shut behind you, the environment changes instantly. The air is cool, still, and completely quiet, devoid of the loud, cyclic vibration of an air conditioning compressor. There are no drafts of stale, recycled air. Instead, there is only a gentle, continuous movement of fresh, earth-cooled breeze. A digital thermometer mounted on the central adobe wall reads a stable, comfortable 74 degrees Fahrenheit. The data loggers hidden within the walls and shafts of the home tell the true story of this thermal transition. When we plot the temperature readings on a graph, we see two starkly different lines. The outdoor temperature line is a wild, sweeping wave, climbing rapidly from a pre-dawn low of 66 degrees to a midday peak of 106 degrees, a massive swing of 40 degrees Fahrenheit within a single 12-hour cycle. But the indoor temperature line tells a completely different story. It is a nearly flat, stable path, hovering between 72 and 75 degrees Fahrenheit throughout the entire 72-hour period. This represents an indoor temperature fluctuation of only 3 degrees, completely decoupled from the violent swings of the outdoor environment. This extreme stability is the direct result of thermal lag and the continuous convective air exchange driven by the solar chimney. By measuring the velocity of the air moving through the subterranean earth tubes, the sensors record a steady flow rate that equates to approximately 10 air changes per hour. This means that every 6 minutes, the entire volume of air inside the home is completely replaced with fresh, pre-cooled outdoor air. This continuous flushing of the indoor envelope prevents the accumulation of stale carbon dioxide, moisture, and indoor airborne pollutants, maintaining an air quality level that rival or exceeds most mechanically ventilated modern buildings. But the data also reveals the strict physical limitations of this system specifically, the phenomenon known as the relative humidity trap. Passive evaporative cooling towers work by converting sensible heat into latent heat. When dry air passes through wet cooling pads, water evaporates into the airstream, absorbing thermal energy and lowering the dry bulb temperature. However, this process also increases the relative humidity of the incoming air. During the first 48 hours of our test, when the outdoor relative humidity remained below 15%, the cooling tower performed exceptionally well, dropping the incoming air temperature by over 25 degrees. But on the third day of the trial, a localized summer monsoonal flow pushed the outdoor relative humidity up to 45%. The data loggers captured the immediate thermodynamic impact. Because the air was already saturated with moisture, the rate of evaporation inside the cool tower slowed dramatically. The temperature drop inside the tower decreased from 25 degrees to a meager 8 degrees. The indoor air became heavy, humid, and uncomfortable, demonstrating that in climates with high ambient humidity, pure evaporative cooling quickly loses its effectiveness. This is why the integration of subterranean earth tubes is so critical. Unlike the cool tower, which relies on evaporation, the earth tubes cool the air through direct, sensible heat transfer with the cool earth. Even when the monsoonal humidity spike crippled the cool tower, the earth tubes continued to deliver cool, dry air to the home, allowing the occupant to close the cool tower dampers and switch the home's intake entirely to the subterranean loop. This hybrid functionality is what separates a scientifically engineered passive home from a simplistic, single-system design. It proves that by understanding the psychrometric chart and knowing when to shift between sensible and latent heat rejection, we can maintain comfort throughout the shifting phases of the summer season. As the sun begins to dip below the rugged western horizon, painting the desert sky in shades of deep amber and dusty violet, the solar chimney's glass face catches the last rays of golden light. The intense convection draft of the day slowly begins to ease, transitioning into a quiet, low-velocity nighttime cycle. Looking at this structure, standing quiet and self-sustaining in the vast desert expanse, we are reminded of a deeper philosophy of architecture. For nearly a century, modern home construction has been defined by a philosophy of confrontation. We build lightweight, thermally transparent boxes, and then we use massive amounts of electrical energy to force those boxes into habitability. We fight the local climate with high-wattage machinery, and we assume that the grid will always be there to power the battle. But the old miners of Tombstone and the ancient builders of Persia understood a more sustainable truth. They knew that the most resilient structure is one that cooperates with local physics rather than fighting them. By utilizing the natural buoyancy of warm air, the constant thermal capacity of the earth, and the latent cooling power of water, they constructed shelters that functioned as natural thermodynamic engines. They didn't need to conquer the desert heat. They simply learned how to use its own energy to drive a cooling loop. Yet, as we look to apply these historic lessons to our modern lives, we must carry a sense of deep humility and realistic responsibility. Passive engineering is not a simple weekend craft project, nor is it a magical shortcut to a zero-utility life. It is a precise, unforgiving science that requires careful calculations, quality materials, and a strict adherence to safety protocols. A single error in calculating a chimney's height-to-width ratio can stall your draft, and a single mistake in sealing your building envelope can short-circuit your entire subterranean loop. Most importantly, we must never compromise on the vital safety systems that protect our families. The physics of convective draft are powerful enough to reverse heating flues and draw invisible, deadly carbon monoxide directly into our living spaces. We must treat these passive forces with the same respect we afford to high-voltage electricity or pressurized gas. Every passive build must be designed in consultation with professional, structural, and mechanical engineers. Every fuel-burning appliance must be equipped with a sealed, direct-ducted external combustion intake, and digital, battery-backed carbon monoxide alarms must remain active on every level of our homes. By combining the ancient, elegant wisdom of the frontier with the uncompromising safety of modern mechanical codes, we can build homes that are truly resilient. Structures that protect our lives, honor our environment, and stand as silent, self-sustaining sanctuaries against the volatile climate of our changing world.